Hi, everyone. I hope that you're all doing well. Welcome to the fourth lecture in my series on statistics for the social sciences, or for sociologists, as the course is formerly known at UW-Madison. Here's what we're going to cover in this lecture. We are going to do a little bit of review in the actual in-person version of the course, but in the tape series, I've already covered the entirety of lecture 3, so we'll begin with distributions generally, which we hinted at last time, but we only discussed really certain ways of measuring the spread of a distribution, so the 5-number summary or the variance and standard deviation. But today we'll discuss distributions overall, and that required us to go back to the concept of functions, and we'll discuss some kind of unusual functions, so some piecewise functions, some nonlinear functions, but they'll be functions in the same sense in which you learned about functions in algebra, and especially algebra 2. We'll start with what are known as cumulative distribution functions, or CDFs. Then we'll discuss probability mass and density functions, PMFs and PDFs. This is not discussed formally in our book, but I found that it's very helpful to just get a whole picture, learn a little bit of jargon that'll really set you up for success. The book sort of tries to skirt these issues, and it tries at all costs to avoid going into any more detail than is strictly necessary, but I found that that approach in the long run actually tends to harm students, if for no other reason than, one, it makes it very difficult to search the internet for information because this terminology is utterly standard, and two, sometimes showing people how certain concepts, such as that of a normal probability density function, relate to other concepts, even if we're not going to directly use them, is oftentimes a great improvement on just learning the bare minimum. And I've been teaching this class for a long time now, and I think I've had more success when I've, generally speaking, taught a little bit of the detail. Then we are going to focus, however, on the normal density curve or probability density function. They mean the same thing. So we'll look at a worked example, one that's approximate, one that's exact, and then one that's got kind of a twist on it. So here's the summary of the lecture. What we're going to focus on today are primarily probability density functions for continuous variables. These show us the probability under the curve of a numeric range of the variable. So in other words, areas under the curve of these PDFs, or density curves, are the probability that a random variable will take on a value between the 2 points that you're taking the area. So it's helpful to contrast them with cumulative distribution functions, which I'll explain shortly, and probability mass functions. Probability mass functions are a lot like PDFs, but they work for discrete rather than continuous variables. Both of these have cumulative distribution functions, although they look different for each type of variable. The next point here is that some variables have a very specific distribution called the normal. The normal probability density function is bell-shaped. So if you've seen the bell curve or the Gaussian curve before, that's formerly known as the normal probability density function. It's got some nice properties. Its mean is its median, and its shape is given by a well-defined equation about which we know a lot. It's also symmetric, and it can be easily standardized to have mean 0 and standard deviation 1. More on that later. Areas under the curve of a normal PDF are tough to find with calculus, so your standard Calc 1 methods won't work very well. And instead, what you need to do is use polar coordinates and use some methods that generally come from multivariable calculus. So we're going to skip all that and just use a table of cumulative proportions from the normal CDF. So that's a reason to learn the CDF, is that the table we'll use to calculate those areas actually comes from a different function. And typically, it's not told to students where those values in the table come from. And I found that tends to confuse people because they start to think that the table has values that come from the curve they can see visually. And it turns out that it comes from a different, although closely related curve. And I found it easier to just spell all of that out. One thing you should do, whether you're in my class or you're just generally hoping to get acquainted with statistics, is to memorize some common areas under the curve. So we'll see here that mu later on means the mean at the population level of a given random variable. And if any random variable is normally distributed at the population level, that means that within plus or minus 1, 2, and 3 sigma here means standard deviation, the lowercase sigma, of its mean will contain 68, 95, and 99.7% of the area under the curve. And recall, as I said before, that we can standardize any normally distributed variable, and this makes it very easy to find the probability of a value less than it or greater than it, or between 2 points. So finding it here probably should be than some value, but you get the point, despite my sloppy grammar. And then the standardization process is very simple. We simply subtract off an arbitrary mean from a random variable. We divide out by an arbitrary standard deviation, and we're left over with the z-score. You can generally standardize the entire variable, or you could just take the standard score for a particular observation. And then finally, the way that you find the areas under the curve is that you'll look in what we call table A, sometimes also called the z-table, for the area to the left of the curve, and then you can perform further calculations as needed. So that gives you the area under the curve to the left in that table, but that also allows you to find the area under the curve to the right through the kind of complementary rule, or you can find the area between 2 points, and we'll see that that reduces to simple arithmetic. So what are distributions generally? Distribution is a generic term for the relative frequency of the values of a set. So basically, which values are more and less common. There's 3 representations of distributions that we'll find useful. The first is the cumulative distribution function, which exists for all kinds of variables, or almost all kinds. Probably there's some exceptions. And then the probability mass function, which is defined well for discrete variables, and the probability density function, which is defined well for continuous variables, and only the last of which our book directly discusses, although you'll see that again, results from the CDF pop up all over the place in our book. So let's formally define these things. And this might seem a little bit scary, but I think it's helpful, and we'll see some nice intuitive pictures in a moment. So the cumulative distribution function of x, big F of x, is equal to the probability that the random variable x is less than or equal to some particular realization. So in general, I try to be consistent about this, but it's not always consistent in the literature unless you're reading a formal textbook. But generally speaking, large Roman alphabetic letters will mean random variables, especially those near the end of the alphabet. And if you see the lowercase version of that letter, that typically stands in for some realization of the variable. It's a little confusing, and that's kind of a tricky thing generally to represent realizations, which are by definition concrete, as something that's abstract. So that's one reason that we write this little lowercase x here. It's to say this stands in for some generic observation of the variable, whereas x is just the random variable in all of its full random glory. So cumulative distribution functions of x have as their height is just big F of x here. And big F of x doesn't have any special significance. We just write it with a big F for reasons I'll explain in a moment. But it basically, you can think about it as the y value, or the output, is equal to the probability for some given x value that the random variable x is less than that value. The probability mass function of x, which you can write like this, little p of x, where p is just some generic function, is again equal to the probability, that's what this big blackboard p means, that the random variable x is equal to some specific value. So in this case, the height of the function, or the output of the function, for some particular possible realization of x, which we write with little x, is equal to the probability that the random variable takes on that value. Finally, the probability density function of x, which might seem even a little bit more challenging, this is little f of x. And this we sort of have to define in a funny way, although you'll see that it's actually quite intuitive. So little f of x here is defined so that the probability that the random variable x lies between 2 points c and d is equal to the integral between points c and d of little f of x. And the integral you can interpret in this context to simply mean the area under the curve of this function here. You can ignore the dx here. That's kind of a hangover notation from the early days of calculus. But if you don't know calculus, just see this. This is actually a big elongated s, and it just means sum up between c and d the area under the curve of f of x. And you can almost think about it as like the height times a tiny little increment in the width, which is actually what that dx means. So don't let this scare you. It just means sum up the area under the curve of f of x between c and d. So let's examine some cumulative distribution functions and some probability mass functions. So let's look at some examples of cumulative distribution functions and probability mass functions. Cumulative distribution functions, as I note here, are defined for discrete random variables and also for continuous random variables. Probability mass functions will really only make sense for discrete random variables. So let's look at the figure on the left first. So what this shows us is the cumulative distribution function for the number of children using data from the GSS 2018. So this is a random sample from all US adults. That's the population of interest, and then this is the size of the sample here. So this graph might look a little bit unfamiliar, but it's actually surprisingly easy to read. On the x-axis, we have possible values of our variable, and on the y-axis, we have the probability of observing a value of that variable less than or equal to whatever the given value of x is. So in this case, we would say, and by the way, probability in this context, although probability can get pretty complicated, what it means here is effectively identical to what you believe to be the long-run frequency with which a given event will occur relative to other events. That's a pretty abstract definition, so let me give a particular example. If I tell you that the probability of rolling a 5 when you roll a fair 6-sided die is 1 in 6, what I'm telling you is that the probability in my estimation, or if you want to use a kind of physical notion or some kind of basic physical law about how dice fall, that the frequency in the long run with which you'll get a 5 is 1 in 6. You can convert that to a percent or a decimal if you want, but you can leave it as a fraction. So that's effectively what probability means in many contexts. Not always, and sometimes the distinction between, say, a subjective belief about the world and something that you think could be grounded in physical fact is important. But for most purposes, when you hear probability, if you just think the percent of the time that some event occurs. So again, to pick a simple example, if someone says the probability of flipping heads when you flip a fair coin is 50%, they're telling you that if you flipped a coin often enough, that heads would occur about 50% of the time. That's a fine intuition. So let's go ahead and read this graph in this case. Let's just pick a kind of random point here. Let's say we pick the point 3. So what this graph is telling us is that for the value 3, the probability of having a number of children less than or equal to 3 was about 0.8, let's say 6 or 7. If we pick another point, let's just kind of, again, randomly select one. Let's pick this point here. So this is the value 1. So what this is telling us is that the probability of having a number of children less than or equal to 1, so the probability that someone had 0 or 1 children, or child, I guess, is equal to, it looks like about 0.42 or 3, something like that. It's a little bit hard to judge. And so that's how we would read this function. And it's kind of surprisingly easy to interpret. I wanted to call attention to just 2 points. First, note that the graph here is flat for non-integer values because those aren't really members of our set. And in a certain sense, we don't even really need to plot this. You'll see in a lot of cases, people will plot CDFs in ways that use standard plotting techniques that are oftentimes very misleading. So sometimes you'll see, for instance, vertical bars here too. I don't want to get into the details of those in this discussion, but let's just say that for a discrete random variable for the CDF, the only values as inputs that really make sense are the possible values of the variable. Nevertheless, it's pretty conventional to show these here to show that the probability is flat, because as we go from 1 to 1.5, etc., because children is a discrete variable and children don't come in halves, the probability doesn't increase. Notice also the hollow circles here. What this is showing us is that the probability does jump up rapidly when you go from not 1, 1.5, 1.6, etc. But when you get all the way to 2, then the probability jumps because there are a large number of people that have exactly 2 children, meaning that when you go finally to the next possible value up to 2, there's a big chunk of people there. And what this is telling us actually is that there's about 30% of people, give or take, depending on how big this interval actually is here, that have exactly 2 children, because this gives right here the probability of having 1 or fewer. This is the probability of having 2 or fewer. So the difference between them has to be the probability of having exactly 2. And that gives us an intuition for how to read this graph on the right. And this graph on the right, you can actually read very much like a bar graph. And indeed, this is essentially just a bar graph. So this is the probability mass function for the number of children. And as I mentioned in the last lecture, those 2 things fundamentally come to the same thing. What this shows us is something actually a little bit even easier to interpret. We've got on the x-axis the possible values of the variable. So again, 0 children, 1 child, 2 children, etc. Then on the y-axis, we've got the probability of any of those given events. Notice that because 0 is the smallest value of the variable, the cumulative probability and the probability of having exactly that number of children should agree exactly, and notice that they do. And we can see here that the heights at any point of this function should be the sum of the heights up until that point. So if we look at this here, this is like about 0.28, this is about 0.15, right? So if you sum those up quickly, you should get something around 43, and that's right what we get here. And you can kind of see so on and so forth. I wanted to call attention to sort of two more points here. First of all, the cumulative distribution function does eventually need to hit 1 because the entirety of the sample will have been observed. This is an estimated cumulative distribution function, by the way. And so we do hit 1 here. And you would see if you summed up these heights that they would sum to 1. And you should also notice that this can never go below 0 on the x-axis if you have certain common types of discrete random variables that don't take negative values. So there's a reason that the graph is bounded here. Again, so the y-axis for this graph here, the CDF, is the probability of having a given x value or one smaller than that, and the probability of the y-axis, pardon me, of the PMF here is the probability of having an exact x value. So notice also that, for instance, this function is not monotonic. We swap in these values 0, but then we go down to 1 because 1 is less common than 0. Then we go back up to 2 because 2 is more common than 1, still less common than 0. And so you can kind of see you have, if you were a GSS answering adult in 2018, you obviously had a probability of having 1 or more children that was much greater than having 0 children. But notice that the most common individual situation was having exactly 0 children. And that kind of makes sense. There's only one way to be a childless adult. There's many ways to be an adult who has a child. But that's a kind of difference here. This function doesn't have to be monotonic. In other words, it can kind of go up and down. It doesn't have to always increase. Here, however, this function always has to increase because it's cumulative by definition. So the probability that you'll have, let's say, 2 children or fewer, at most, the probability that you would have 3 children or fewer right here could be exactly the same. So if that somehow improbably were the case, and this dot would move down here, it could never go negative, or it could never turn negative. So in other words, you couldn't have, say, exactly 70% of the sample that had 2 children or fewer, but then somehow 68% of the sample that had, say, 3 children or fewer. That doesn't make any sense logically. So that's how we read CDFs and PMFs. And this writing here gives some other examples, but I like to explain without having the text up. And as I mentioned here, a PMF is basically a bar graph or a discrete histogram. And the areas in bar graphs and discrete histograms don't really matter much. They could even be distracting. So sometimes you'll see it represented as these dots. I recommend, by the way, in the footnotes, some reading from Orloff and Bloom, who are professors at MIT who have a really excellent accessible intro stats course. And I decided to use Python to plot the CDF and PMF in this way because Stata doesn't really allow for a truly exact way to plot these things. I'll show where that is, by the way, in a second here, if we can kind of get the footnotes pulled up. Sorry about that. It's kind of useful information. So if you come down here, you can see the code, and I'll show how you look at that. So one nice feature of Python, which you don't need to use for this lecture series to be able to follow it, although I will show graphs from it pretty often, is that you can publicly put up code. So this is just linked to my GitHub, and you can see all the code that I wrote here to come up with this graph. So if you're interested, that's what that shows. Okay, so let's proceed onward to a discussion of probability density functions. I need to hide my floating meaning controls. Sorry about that. So let's pull up a graph here. So probability density functions, by the way, let's start with cumulative distribution functions, actually. So we're looking at continuous variables here. And cumulative distribution functions also exist for continuous variables. And in theory, at the population level, they should have this nice smooth shape. And if you have, fine enough measurements in a particular sample on that random variable, even the estimated CDF, you can see that's what this step-like function is here, will ultimately have a shape that is getting relatively close to continuous or smooth, I should say. So notice that this does resemble in some ways the CDF that we saw on the last slide, but it's significantly less linear, basically, or less piecewise. I also went ahead and plotted an estimate, one way of estimating this. So I use the example of height here, which is a variable that happens to have a distribution that's very close to a well-defined CDF and well-defined PDF, which is the normal distribution. So I plotted, in this case, the normal distribution in the background. And you can see that that is one guess at what the population might look like. Although, again, the population isn't really, strictly speaking, known. But what we could say is we think that the data are drawn from a distribution that's fundamentally this smooth one here. The smooth one is in the kind of checked line here. So the interpretation of the cumulative distribution function doesn't change. So we would say here, if we look at the value of a given or a given value here, say 68 inches in height, we come up here. It's a little hard to trace it up, but we're going to say that whatever the height of the height function is here, I think it's this one. My eyes are a little bit old. Maybe it's this one. So it looks like about 50% of the sample, or maybe 57%, something like that, was 68 inches or shorter, meaning that we estimate that a person had a probability of 56, 57% of being 68 inches or shorter. And if we come up to like 73, we can see that the probability, again, not having an easy time tracing, might want to put a grid line in this in the future, comes to about 90% and so on. So that interpretation doesn't change. Now here on the right, we have the probability density function for height. And probability density functions are different than probability mass functions, and this is pretty important. So here's a couple of ways to think about it. First, I want you to note that if you have a truly continuous random variable, remember that that means that there's an infinite number of possible values. And if you really think about it, the probability of having exactly any one of those values is extremely small. And actually, we formally say that it's 0, which is a little bit confusing. But if you really think about it, if you truly could measure, I mean, for one thing, it means that there's, it's really impossible to fully measure all of the possible values, because we would need to never stop writing down the decimal of height, for instance. So we couldn't just take it to the millionth place or the billionth place. We would need to take it all the way to the end of the real numbers, which is not possible. So that's one kind of intuition. The second intuition that stems from that is, even if you could somehow write down all of those numbers, then what's the actual probability of having any one of them, right? So it's going to be one of this infinite set of numbers, and you don't have to really get exactly why it's 0, but you can just probably intuit that the probability of observing any one of those possible values is extremely small, unlike a case where you know, the only reason you would observe in a discrete case a probability for a given value being 0 is if there really just were no people that ever took on that value. But you can see here that if you think about taking a value here, like let's say 63, and let's say we pick 63 point a trillion zeros and then a 1, right? So what's the probability of someone being exactly that tall? And again, in theory, we could measure to that precision, we just don't, but that's what makes it continuous. We kind of get an intuition that the exact height on that curve is just going to vanish at some point. So if the heights of this function aren't really that important, what matters? Well, what matters is the area. And I want to now kind of tell you why that is. So I haven't really talked about what this term density means. I talked a little bit about it last time. But what density is actually probability per unit. So what this graph here is on the right is a graph of the rate of probability change per unit. It's actually a graph of the speeds of this thing. So if you look at where the heights of this function are tallest, from about 58 to 73, that's where this thing really starts to pick up steam and then finally starts slowing down. In calculus terms, although I don't want this to scare anyone, this graph here, the PDF, is actually a derivative of this graph, the CDF. So this graph here contains as y values all of the instantaneous rates of change for a given value of x that we observe on this graph here. If instantaneous freaks you out, just think the slope in a very narrow region, basically, which is formally what it is, just take it to the limit. So that's how to interpret this. So then what actually matters here? Well, it's not the heights, which are probability per unit or density. It's actually the areas under the curve. So if you think about filling up an area under the curve, say from 63 to 73, you would do that by taking a bunch of slender rectangles, very slender rectangles. And you would have a rectangle, like let's say right here, that's got a width that is just some unit. It's height, although the units don't really matter because they're going to cancel. And then we've got as the y value some probability per unit change in height. And then if we think about taking the rectangle, so we would take the height, which is probability per unit, and then the width, which is unit, multiply them together, and we get an area that represents, well, probability because the units canceled out. So it's the area under a density curve that matters. And we would see that, for instance, if we could take the area under this curve from about, let's say about 58 to, let's say about 78, somewhere in there, and being a little loose, we would find that the area under that curve is somewhere in the ballpark of 0.9, meaning about 90%. And we'll see later on that there's a class of function or a class of PDF known as the normal, where it's still actually really hard to take the area under the curve using calculus, but people have done it in the past. And it's actually easy with computers, but it's just challenging for reasons I'll hint at a little bit later. And so we can be more exact, and that'll be really useful to us later on. And this is some stuff I just said out loud. So I want you to notice that histograms and probability density functions are closely related. So a density histogram that we saw before is an estimate of the true probability density function just using sample data. We'll come back to the sample to population inference problem later, but that's the basic intuition. The thing, though, is that for the type of histograms that we make, area isn't really that important because we're not, as we saw last time, we're not actually changing the graph when we scale it to mean density. It's still got the same shape as a percent histogram. And the thing that's happening here fundamentally is that we can't actually observe a truly continuous random variable in reality. We can know that our variable is continuous because there in principle is no limit to how precisely we could measure it. But we always have concrete sample data. So we always have a limited set of sample data that are measured to a limited precision. And that means that we are never going to observe these nice smooth curves like this black one here. Now, what we can do many times is we can estimate a smooth curve. So one that doesn't look like a histogram, which has these kind of bar shapes, basically, which is why it's often confused with the bar graph. And the way that we estimate this nice smooth shape when we know that it would be appropriate, in the case of height, it would be appropriate because height is truly continuous. So we know that the population function will look smooth. What we can do is we can estimate it using this method known as kernel density estimation, which produces, in this case, a curve that looks pretty similar to this normal curve. A little bit different. It's kind of got a little bit of a smushing in here, but you can see that it looks roughly the same. So kernel density estimation offers a nice way to try to get at the true probability density function of a continuous random variable based on sample data. And this is a reason why I recommend against actually using density histograms before, because the problem is that we're not really doing anything different to if we just make the area, if we just worry about the heights of the bars being percent, we're not really giving much intuition by showing the area as being the area of the bars summing to 1, because all we're doing is rescaling the axis. So these probability density functions are super cool, but they're cool at more a population level. And you'll see later on that most of the use we get out of these probability density functions is kind of meta in a way that we'll come back to, but we don't often know the PDF for a random variable. We know the PDF about, say, the distribution of a variable across many different samples or properties of the variable, such as the mean. So that's just a bit of a preview of where we're going to go. Now, let's talk about a curve that will become very useful for us later on for exactly that kind of meta statistics, which is actually what all of statistics is really about. But it also describes some real-world variables well, such as height. That's the normal density function, oftentimes just called the bell curve or the Gaussian distribution. And again, as I just mentioned, we're going to use it in mostly a meta way, but it does sometimes work. So it's this shape here. This is the standard normal curve, actually, which has a mean of 0 and a standard deviation of 1. We don't need to worry about that for now. and it has this nice pleasing shape, and it doesn't seem like there's too much complicated about it. And that's actually true in many ways. There's not. So here are some key facts about that normal distribution, and I want to pull up the picture first here. So it's symmetric. Its mean is equal to its median. And that hopefully seems pretty visually intuitive. Again, this is a standard normal. It's got a mean of 0. That means that the median is also a 0. And we can check our intuition here by seeing that the equal areas point, which we know is the way we define the median, also appears to be the balance point for the curve. It seems like it would balance here as well. It's also got a mode that is, although we don't exactly care about the mode here with the density curve, because again, the mode would just be a single height rather than an x value. But the mode here is appearing to also be at 0. It's bell-shaped, which is not super precise, but you can see it kind of looks like the Liberty Bell or something like that, a bell viewed from one side. The key parameters, and here what this means is the things that make this normal curve, this one here, different to any other, are the mean, mu, and the standard deviation sigma. I want you to note the population notation here. So this, again, is the Greek letter mu. It makes the M sound, even though it looks like a U, so you can remember that it stands for mean. And this is the Greek letter sigma, lowercase sigma, because capital sigma means sum. Here, this means standard deviation. Again, it's a Greek letter, so Greek letters for us will mean population parameters. And again, these things are typically not going to be known by us. But there are some curves where the parameters aren't really, say, things we think are true of any variables. They can also be just conceived of as things we plug in for convenience. And that's what's happening with the standard normal curve. So just for the sake of convenience, we can define and use a curve that's got mean mu of 0 and standard deviation sigma of 1. And basically the way that those work is that the location of the distribution, so where this is on the x-axis, is given by mu, and sigma governs the spread. You would see, if you actually look up the normal curve, which is a kind of monstrosity, it's, if you're ready for this, 1 over sigma times root of 2 pi. All of that is taken to, or multiplied by Euler's constant, all of which is taken to the power of negative 1/2 times x minus mu over sigma, all squared, which is pretty complicated, and it took me a long time to learn how to say that without needing to go look it up. But you would see that it's a function, right? There's a place where you could just plug in mu and sigma. And I want you to also note this kind of distributional notation too. So if a variable z has this standard normal distribution, we can note this as this. Again, note the distinction between the capital Z representing just the random variable as a concept, and then possible values of Z, which are given here on this x-axis. So the main things to know out of that's a lot of facts, would be that the mean and the median are the same, and the mode as well is also right in the middle there too. And that all normal curves in principle look the same from a certain angle, zooming out enough, but they've got different means and standard deviations. Now, here are some key facts about those areas under the curve, which I mentioned before can be approximately known for arbitrary probability density functions, but which are known exactly for normal curves. So the area under the curve between mu minus sigma and mu plus sigma, in other words, within plus or minus 1 standard deviation, is about 68% of the distribution. So the darkest red here is 68% of the distribution. The area under the curve between plus or minus 2 standard deviations, which is the most commonly cited area under the curve, you'll see why, although it'll take a while to unfold, is about 95%. So that's sort of in this reddish pink here. And then the area under the curve between plus or minus 3 standard deviations, so by the way, these are cumulative, so this reddish pink includes the red as well. This lightest pink, also including the entire area here, is about 99.7%. That's sometimes known as the 68, 95, 99.7 rule. So as I mentioned before, every normal distribution can be seen as a transformation of the standard normal. And we can turn any score from any normal into units along the standard normal by subtracting off its mean mu and dividing out by its standard deviation sigma. We call that a z-score or a standard score, and it's given by the formula z is equal to x minus mu over sigma. And what this gives us is the number of standard deviations a particular score is from its sample mean, which is kind of a cool fact. And the reason for that is that because taking a standard score takes some actual value of a variable and turns it into a value on the standard normal, because the units of the standard normal are in standard deviations, 1 unit along the standard normal is also equal to the standard deviation of that thing. That means that any standard score can be interpreted as the number of times of the standard deviation you are away from the mean. So here's an example of a kind of particular normal curve. It's just one I picked at random. It's got mu of 9 and standard deviation of 15. You can see here that it's centered at 9, and that if we look at the area under the curve, that looks like it's about 95%. It's going out 9 plus or minus about 2 times 15. So if we actually did that exactly, we would get 9 plus 2 times 15, or 39, and then 9 minus 2 times 15, or negative 21. In fact, the actual values here are a little bit off, and this is a one case where I do want you to know the exact numbers, because it can sometimes make a difference. But we're actually not, in this case, plus or minus 2 standard deviations, we're plus or minus 1.96. And if you want to get really exact, it's 1.959, and then a bunch of numbers that are really close to 9 or 8. But what that means is that basically the rule holds true. So within about plus or minus 2 standard deviations of the mean, 95% of the data lie, or 95% of the area in the curve lies. And we'll see later on that these can be interpreted to give the distributions for real variables. So this is just one particular example. So the way I got these coordinates here, by the way, is you just solve this z-score equation here. So the way that you would do that in this particular case to figure these out is you would say, well, I want a standard score that's about 1.96. I know the standard deviation is about 15. So let's just say this is 2 for the sake of easy mental math. So I take 2 and multiply it by 15 to get 30. And then I know that the mean mu is 9. So I'll add 9. And then I'll also subtract off 9 because the curve is symmetric. So that's how we would get this here. And you'll notice that solving that standard score equation for some value of x by multiplying by sigma and then adding mu to it, or we can later on subtract mu. Again, you don't have to do that. You can just know that the thing is symmetric. So if you'll add to one side 20, in this case, roughly, then you'll subtract 20 to get the other coordinate. That gives you these actual values for this particular normal curve. So I wanted to just bring this back one more time to this kind of nice fact about the normal curve. I mentioned this before, but it's a little bit hard to fully understand at first, but it's actually a really deep and beautiful property. So density is a little bit hard to interpret. Again, we've already seen that the area under the curve interpretation is really nice. But I want you to notice that the CDF and the PDF are really simpatico. They have a nice shared property, which is that they tell us about the distribution of the variable. And the reason that we care about the area under the curve of the normal, again, is because the exact height, probability per unit, is hard to interpret. It's got a nice mathematical interpretation. The substantial interpretation is sort of that it's the speed of probability, which is still somewhat hard to kind of get your head around. And it's also really not clear that the concept is like well-defined for what's well-defined, but it just happens to be 0 for any particular value of the curve. But note that if we just instead think about the area under the curve between 2 points, we can say a lot about that. And I want to try to show you why that is. And again, I want you to think about taking the area under the curve here. So if we take the area under the curve right here, again, what we would be doing is making up those slender rectangles. So those rectangles would have a height that's equal to probability per unit, and then a width that's just equal to units. And then if we think about making the rectangles very, very small, they would kind of eventually, I know it takes some imagination, but you want to think about making them so tiny that they almost look like lines, and then at a certain point, they would become visually indistinguishable from just shading in like I've done here. So what does that represent? Well, if the height is probability per unit, and then we've got also here multiplying it by units, well, notice that on this graph, we have cumulative probability. So probability per unit is represented as a little slope here, right? So it's the rise over the run, if you want to think about it like that. And then if we think about multiplying those rises over runs by x values, which are just runs, right? We're just going to get rises. So those are going to basically give us the total change in the curve. So notice this really interesting fact here that if we look at the CDF for the normal curve, notice that at negative 1.96, it's 0.025, and at 1.96, it's 0.975. So what's the difference in heights there? Well, that happens to be exactly 0.95. The area under the curve here between negative 1.96 and 1.96 is 0.95. So that's a really cool fact. And what that tells us is that we can conceptualize these two graphs as showing us fundamentally the same thing. The difference in heights of the cumulative distribution function between z equal to sum c and z equal to sum d, here those are negative 1.96 and 1.96 respectively, that's equal to the area under the curve of the probability density function for those two same points. And actually, that's the fundamental theorem of calculus, if you're interested. That's quite literally just a classic, no funny stuff example. It's an example that could be shown in Calculus 1 classes. In fact, I think it's actually quite interesting and gives a really nice way to think about it. So that's just kind of a useful fact to know. One reason that I bother introducing the CDF, by the way, is that this means of visualizing is very useful. So is this, although it's not taught as often. It's taught in every mathematical statistics course, but not always in applied ones. But one thing to note is that this is, if you're watching this lecture, you've hopefully done the reading where you learned a little bit about table A in any statistics textbook. It's actually this function here that gives the values in table A. So table A, which starts usually with like negative like 3.9 or something like that, which you never actually need to use, going up to 3.9 or whatever. Those values are all just heights on this cumulative probability function, or the CDF. So sometimes that confuses people because we get used to looking at this shape, but then the numerical tables that we use come from this function instead. So it's nice to be able to see the connection. So how is this information actually useful? If we happen to know that a variable is normally distributed with arbitrary mean and standard deviation, we can standardize it, and then that'll give us the area under the curve between 2 points, which is the probability of data between those two values. And for that, we use this table A here. And I guess the table goes up to 3.49. I hadn't actually looked that far in the table in a long time. In practice, once you get to a certain level, you don't need to use this table. You can use computer functions, but it's a lot of times easier to give people something nice and tactile to put their hands on. So that's the primary use of the table. Let's think about some examples here. So again, because we don't necessarily care about the probability of a single point, and it's really not possible to say what it is unless you just want to accept it as 0, which most people find confusing, we can just say, well, why don't we find the probability of a range of values, or the area under the curve between those 2 points. So let's look at a concrete example. Let's use my height as an example. I'm 74 inches tall. Let's find out what percent of people are taller than me using estimated data, assuming that our two key population parameters are the same as the GSS 2018 sample estimates. In other words, let's assume that that sample data that we have from the GSS is just as good as population data. So there, that would mean that mu is equal to 67.15 and sigma is equal to 4.14. The mean is 67 inches more or less. The standard deviation is 4 inches more or less. So we would start by finding the z-score, and then we're going to standardize this approximately normal distribution. That could mean taking the true mean, mu, away from every observation in the data set and then dividing every observation in the data set by sigma, or it could just mean doing it for a particular point, and that's what we'll do here. So how would we do that? Well, we would say z in this particular case is equal to 74 minus 67.15 over 4.14. That's simple arithmetic, and it gives us this nice number here, 1.65. So now what we're going to do is go into the table. The table is a little bit hard to read at first, but note that these are values in the hundredths place. And so the way we read it is we just go down to 1.6 and then over to 1.65. My old eyes are having a little trouble. Well, we see here that we get 0.9505, also given right here. And so again, this is a table of cumulative proportions. You can visualize it as being given by the left-hand side of a PDF, which is this here, but you can also just visualize it as the height on the CDF up to that point. I personally think the latter is a little bit more intuitive, based on what I found confusing about the fact that this is not giving the middle areas of the PDF, it's giving the left areas. But again, that's because they come from the CDF. So what does that 0.9505 tell us? It tells us that there was a probability, in this case, of someone having a height of mine or smaller equal to 0.9505. So if we want to find the probability of someone being taller than me, if the probability of someone being as tall as me or shorter is about 95%, logically that means that the only probability remaining is that number taken away from 1 or 100, depending on how you want to conceive of it. We'll usually use probability integrating to 1 in this class, but you can also think about it as 100%. Just be careful of the context. So the final answer is easy to compute. It's 0.0495, which taken from a decimal to a percent means about 5% of people were taller than me. And we can visualize this with a really helpful online tool. So we're going to head here. And you can make these kinds of graphs that I'm making in Stata, but you don't probably want to go murking about in those waters quite this early in your career. So this is a really cool tool on David Lane's website. It's called the Online Statbook. And what we can do here is plug in values to change this normal curve here. So notice that I can plug in arbitrary things. Let's just say 73, and then, I don't know, let's just say 9. So you can see this gives a normal curve with mean 73 and standard deviation of 9. Notice that some values aren't possible, so I can't put a negative here because the concept of negative standard deviation is impossible. At most, all values in the set are the same, in which case it's 0. But otherwise, this is open to interpretation. I can even put 99 in here if I want. It's going to look pretty silly, right? So you can see the range on the curve is huge. But yeah, it's kind of nice that you can use this in this way. So let's use a standard normal curve, because that's part of the point of standardizing. Well, actually, let's go back to our original curve first. So let's put in our original mean, 67.15, and then our original standard deviation, 4.14. And then let's put in the tool here, let's say above 74 inches. And you can see that we get the same number that we got by hand. Now we could go below and see that these sum to 1, and they do, which is nice. And then notice we can also find the area under the curve between 2 points if we wanted. We'll come back to that later on, but that's fundamentally how we use this tool here. So you can see a printout of the results in this case. So this is really nice. Now here, I went ahead and actually standardized the curve. So because we already found the standard score, we actually don't need to change this from what it was. So notice that the default is the standard normal curve, and we can just put in our z-score here because that's a standardized score, and we get the same numbers. So here's an approximation using our data. Our data are not exactly normal, so this curve here is not exactly normal, but you can, with a little imagination, see it as being close to normal. And I got this nice smooth estimation by doing that kernel density method addressed before. So what we can do here is ask Stata to find the number of observations above 74 inches. It gives 3.1%. And for 74 and greater, we get 6.3%. Notice here that we do have to make that distinction because we don't actually have continuous data. We have discrete data. In a truly continuous setting, there's no distinction between someone being, say, 64 inches or greater, the probability that is, or the probability of being greater than 70, I think I said 64, but 74 inches. Let me say that one more time. In a truly continuous distribution, there is no distinction between the probability of being a certain height or shorter than a certain height. So the distinction between P of height being less than or equal to X and P of height being less than X, there is no distinction in a truly continuous distribution. And what that means, by the way, I want to dart back here and point this out because this is a common point of confusion. That means that when we go here into the table and we find the area to the left of this curve, 1.65 here, sometimes people often want to, like, let's say we're trying to find the probability of someone being shorter than me. Sometimes people want to trend down here because they think, okay, well, this gives the cumulative probability, but I want it for someone not that height, but that height or shorter than that height, pardon me. So they step down 1 here. But the problem with that is that this is a truly continuous distribution. And if you think about it, we didn't want the probability of being 1.64 on the z-score or smaller. And that actually leaves out people that are 1.641, 1.642, and so on. So the nice fact is that in a truly continuous distribution like this, we can actually just go to the value for 1.65, and we can just say that that's the probability of either having a z-score less than 1.65 or having a z-score of exactly 1.65 or smaller. That's an important point. By the way, I'll also show in Stata how you could count this. And I will come back to that caveat in a second. So let's count this using Stata. So we can pull up our data here if you want. I'm going to get it like this. And we can say count if height, that's our variable here, is greater than or equal to, how did I do this again? We said, yeah, height. So greater than or equal to 74. And you can see that's, and we need to do one thing here. Here's a common Stata gotcha, by the way. So Stata records missing values internally as being arbitrarily large, even though if it's missing, it happens to look like a dot in Stata's actual backend. So I'll show that really quickly. I've shown this before. But let's find a missing value. It doesn't actually, yeah, sometimes it has these value labels here, but you can see if I click on them, you can see that there's a dot and then some letters, but fundamentally a dot, which doesn't seem like a numeric characteristic, but it actually is represented internally as an arbitrarily large constant. So that's why this is so big. Remember that the GSS was like 2,000 people. It's not the case that half of the sample has a height greater than or equal to 74. It's that I need to be a little bit carefuler with my expression here. So the way to fix that, and this is one of the most annoying Stata gotchas I will concede, is to say this, and not missing, exclamation mark works for not. Also, so does a tilde like this, but I think the exclamation mark is clear because it's not as overloaded. And say not missing height. This will make it much smaller. We get 87. Okay, so now let's just count all the people who have a value for height. So we'll just say count if, we can just use our previous expression because now we just want to count if not missing height. So 1402, and now we can just say display 87 divided by 1402, and we get 0.06. So basically about 6.2%, which is, I said 6.3 here for some reason, but I'm not sure what was going on there. So I'll fix that now. And then we can do the same thing for observations above 74 inches. So we can just take away the less than sign or the equal sign here. So we get 44, and then we'll say display 44 over 1402, and we get 0.031, so 3.1%. Notice, by the way, that this is only useful to the extent that the data actually approximate a normal curve here. So we were pretty close. Accounting for the fact that we have discrete data, our answer is that we got using table A was between these two numbers, which is a good sign because it should be, which means that these data are relatively close to normally distributed. But if we have data that aren't normally distributed, taking standard scores can still be extremely useful. We'll see that later, actually, as soon as the next lecture. But it doesn't have the same distributional meaning. It can still be really helpful because it gets rid of certain properties in statistics, like the absolute value of the mean and the absolute value of the spread that are not super useful. What we're actually usually concerned about is the spreads themselves, regardless of where they are. So taking a standard score gives us that vector of deviations that have been standardized. So the vector itself has a standardized length. Yeah, that still kind of matters that you can't use it. Even though, sorry, let me say that one more time. Even though it's a very useful process, that still means that the normal curve approximation may or may not make any sense for your particular situation. Notice that you can also visualize this in the cumulative distribution function as well, which is more directly connected to those values in table A. So again, table A lists values of the CDF, not the PDF, but we can convert between them pretty easily. So here, just like in the table, the probability of someone being taller than me is simply 1 minus the height of the CDF. So you can see here that that would be, in this case, 1 minus this value, which is going to be, again, this is an approximation, but pretty close to 0.05. And then you can see here, this is the actual curve. This is the standardized version, and the standard score here is the answer that we got from before. So it's going to be 1.65, right, which is the number we got. It's a little bit hard to see that because the scale is surprisingly small, but that's in the ballpark there. Okay, so let's look at another example. You might wonder why we bother with z-tables at all, but I wanted to note that it's helpful to have this common language of z-scores because it conceptually clarifies what we're doing. We also didn't really have this level of computing power until recently. So because it's really hard to actually take the area under the curve of, you can't do it easily with calculus. It requires pretty sophisticated multivariate calculus. What that means is that it was really hard to find areas under the curve for particular normal distributions where you've got arbitrary points on it. And it's much, much faster to just know this table of standard scores. By the way, this is the first table of standard scores ever published. This is Crom, published in 1799. You don't need to be able to read the French here. Notice, however, that as I mentioned before, Euler's constant appears right there. You can see, and if you recognize calculus, you'll notice that this is the integral of that function. So in French, anyways. So that's why we have this setup here. Okay, so let's do another practice problem. So question 3.32 in our book, which for those who are not in this course is Mornatz and Fligner, 8th edition, reads as follows. In a study of exercise, a large group of male runners walks on a treadmill for 6 minutes. Their post-run heart rates and blood pressure are distributed normally with mean of 104 and standard deviation of 12.5. For non-runners, it was distributed normally with mean of 130 and standard deviation of 17. So we want to find out what percent of runners have beats per minute greater than 140, what percent of non-runners have beats per minute greater than 140. So you may want to pause the video here and try this on your own, but I'll go ahead and show the solution. So here's how we would do that. What we would first do is find the z-score for the group. I've already forgotten the context, the percent of runners who have beats per minute greater than 140. So we know that the distribution has the mean of 104 and the standard deviation of 12.5. So we would find 140 minus 104 divided by 12.5 and get 2.88. So according to table A, if we come down here, so 2.8 and then scan over to this here, we see that it's 0.9980. So in other words, if you take 1 minus that or take its complement with 1, we would see that there's only a 2% probability of having a beats per minute that high. Then if we do the same thing for, in this case, just to give the context, the non-runners. So the runners basically have very few people that have BPMs that high. But for the non-runners, if we take 140 minus 130 here, so how many of that group, which had a mean of 130 and a standard deviation of 17, had BPMs that high? It was actually quite a few. So the z-score is 0.59. So that gives us the number of standard deviations away from their mean that we are. So we come down here to 0.5, go over to 0.09, and we get 0.7190. So the complement with that is 1 minus that here, which is 27.76. So again, you can draw these. Here's the example for the non-runner group. Notice that these are drawn. In this case, this is with the particular mean and standard deviation of this distribution. Here, this is for the normalized, or sorry, the standardized, not normalized, the standardized distribution here. So we had a z-score of 0.59 there. And notice that these give approximately the same result. We did a little bit of rounding, but they give effectively the same thing, and they appear as the same areas, just under different curves. So you can also figure out what z-scores or even x values correspond to a certain proportion of observations. So let's use the book problem 3.14 as an example. So in spring 2015, the MCAT mean, which is a exam that's given to people that want to go to medical school, was 500 and the standard deviation was 10.6. And let's presume that it's normally distributed. Again, this only works for normally distributed data. So what are Q1, Q2, and Q3? What's the IQR? And what interval contains the middle 80%? So you may want to think about how we would go about solving that. And once again, the key is going to be to figure out the standard scores, which aren't going to change, and then apply them to our distribution using algebra. So here's how we would do that. What we first want to do is get the z-scores to give 25, 50, and 75% of the distribution to the left of the curve, respectively, to give us our quartiles here. And so I didn't show you the left half of the table here because it's too big to fit. I would have no room to write. But because the table A, much like the normal curve itself, is symmetric, we actually don't need it. So if we want to find, like, let's say the z-score that's got 0.25 of the area under the curve to the right of it, all we need to do is find to the left of it, all we need to do is find the one that's got 0.25 to the right of it, and that will appear in here. So we would hunt and peck in the table for a z-score, and you can see here that if we're looking for one that's got 0.25 to the right, it's going to be between these two values here, so between 0.67 and 0.68. And then the z-score for the median, by the way, which is the only one that we still need to find, of course, is just going to be 0 because this is centered at the mean. So we would go halfway between those 2 points, and we get negative 0.675, 0, and 0.675. So again, here, 0.675 that we found in the table over here has 25% of the area under the curve to the right. So it's got 75% to the left. And because it's symmetric, that implies that negative 0.675 has 25% of the area under the curve to the left. And then easily enough, and you can also just see it in the table, the z-score of 0 is the exact median. So those are our z-scores. Now we need to back out the values. So we can plug them into this function here. So in the previous example, we were finding the z-score when we knew x, some value that we cared about, mu, the population mean, and sigma, the population standard deviation. Pardon me. But here we now know the z-score. So like, let's take the first example with the first quartile. We plug in negative 0.675. That's the z-score associated with the first quartile. And then we plug in our two values here for this distribution, 500 and 10.6, and we're just going to solve for x. So when we do that, we follow this process here, and we end up with x equal to 492.85. We can do the same for the other values. I'll let you walk through that. We get an IQR, which is simply the third quartile minus the first quartile, which is this minus this, 14.3. And then our final step here to find the values enclosing the middle 80%, we want to find the z's that have 10 and 90% of the area under the curve to the left of them and right of them respectively. And again, because the curve is symmetric, we can just find this for one side. So to find the area under the curve that's got 10% to the right, we can come down here and let's look in the table, and we want to look for, okay, looks like it's going to be between 1.28 and 1.29. And according to our book at this point, we can basically just round it to 1.28 because this is so very close to 90, which means that 10% is to the right of it. So again, we can back out the x values in the same way as before. We found the z-score that we want. We know the other parameters here, and we just do a little bit of algebra and we solve, and that'll give us those two values there. Notice here that you can also visualize this, which is kind of a nice thing. So in this case, we look at the visualization from the web, which is a little bit less pretty, but accessible to you all. Here I made a figure in Stata, which shows the same thing. And so what this shows us, and this should look kind of familiar now, this does look like that middle 80%. So it's not as big as the 95% that we've seen, but it's the majority of the area under the curve. And it corresponds to those two values that we saw before. The nice thing about this checker is that it automatically prints the middle or the area under the curve selected. So if we look at the area under the curve between the two values that we had, 486.4 and 513.6 with rounding, we see that it rounds to about 80%. So that's where the main part of the lecture concludes. I did want to say a little bit about the optional material. You don't have to watch past this point. So first of all, you can combine box plots and estimates of the probability density function, which is pretty cool. These are known as violin plots. And what these show you is an estimate of the PDF, which is oriented this way here. So you can sort of imagine here like a kind of other dimension where you've got the probability density on one side and then the x values here. So you can imagine another y-axis with density on it, and then on this y-axis here now becomes the x-axis, and it's got the possible heights. And this is also nicely including a box plot as well. The box plot looks a little bit different because you can see it doesn't have the whiskers, but these have the same meaning. So this is the first quartile, the median, third quartile, this is 1.5 times the IQR plus Q3. This is 1.5 times the IQR taken away from Q1. And they're called violin plots because with some of these normalish distributions, these somewhat look like the body of a violin. Not terribly, but sometimes you'll see that. So that's the idea. You could also call them butterfly plots or bird plots, which I think they look a little bit closer to. So that's a cool graphical technique. There's also some stuff you could do with normality. So if you're interested in finding whether or not your data are normal, which is sometimes useful and sometimes not, you can use a quantile plot, which uses the inverse cumulative distribution function that our book mentions, which is a little confusing for it to just mention drop off then after. So let me show the plot first. So this is a little bit hard to interpret initially. I know there's a lot going on. But basically what you do here is you chop up a normal distribution with your variables, mean and standard deviation, into quantiles. And then you do the same thing with your variable. And so what we do here is we feed into a computer program, which you can do in Stata, and Stata does this automatically, the mean and the standard deviation of your variable. And then you can calculate the quantiles associated with the normal. And what you do is you plot on the x-axis here the quantiles of the data were normal, and then on the y-axis you plot the quantiles of the actual data. A black line here is the normal curve for reference, so notice that the line has the same value, the value same as itself everywhere. So this is just the value y equal to x, or the line y equal to x. And then what you do though with this red line here is you plot on the x the quantile if the data were normal, and then on the y, the quantile that you actually see in the data. So let's pick a particular example, and it's kind of nice to see at the bottom end here that we've got some situations where it deviates pretty notably. So right here, you can see this is the grid line. This is the fifth quantile, or the fifth percentile. Percentile is actually a little bit more accurate because quantile is generic. So this is the fifth percentile. Notice that if you had normally distributed data, right, this would be where it would be, but on the y-axis here, the quantile of your actual data, it's a little bit higher. So the reason for that is that this is wages from the CPS, and there's a lower bound with wages that a normal curve with the mean and standard deviation of the data set that we're using does not obey, so it can go into the negatives. But that's not true in the case that you've got, say, wages, because wages can't go into the negative. So you can see here, like for this fifth percentile, it's not possible for the normal curve to have basically, it's not possible for actual values of the data to have what would actually be a wage of 0. It's significantly higher up here. And in fact, there actually are, sorry, I should say this, there's actually people in the CPS that have values of the variable which are 0, but those are probably data entry errors, and even still notice that they can't go below a certain value. They can't go below 0. We can go farther up the curve as well. So notice that it looks pretty normal in the center, but why don't we, again, to kind of understand how the curve works, look at some higher values here. So this is the 95th percentile here. Let's say we go a little bit further to like the 98th percentile. So probably somewhere around it here, maybe even here. So the 98th percentile would have, if it were normal, that quantile would be represented by something like, let's say, $45 an hour. But notice that in the actual data here, it's represented by something like $60 or $70 an hour. And notice that as we go even further, this would probably be like the 99th percentile. That would be somewhere, again, around like, it's a little easier to read on the y-axis here, about $50 an hour. But for our actual data, it's around, like $100 an hour, which is the maximum of our data set. So I know it can seem like a lot here, but basically what this is doing is showing you different quantiles. So this is, you can see, this is the normal curve. It's nice and continuous here, but however many quantiles are here, that's how many it's been split up into. And then there's certain key ones that are marked. So on the x-axis, we have like a particular quantile. So like, again, this is the 5th percentile. So the value on the normal curve here is 1.7 basically dollars per hour. But the 5th percentile on the actual data is this value on the y here, which is 9, then we can kind of go along and see. And when this red kind of caterpillar-like line lies on the same curve as a normal curve, you can see that you've got data that are exactly normal. But in this case, we've got some notable deviations. So there's some left censoring, which means that these are all higher than you would expect if you had normally distributed data. But then at the right as well, you've also got data that are higher than you would expect. So what that means is that we have a lot of bunching at the left end, and then we've got a significant skew at the right end as well, because it's larger in both directions than you would expect from normally distributed data. Here's a little bit more about the histogram versus bar graph distinction. Again, I just want you to note that in reality, percent histograms, bar graphs, the areas don't matter, but even if you have a density histogram, where you're technically saying the area matters, it's generally speaking not that informative. And the reason for that is that bar graphs, again, or histograms that have fixed widths, can't really approximate the smooth functions that we're trying to get them to approximate. So even though you do have actually as a default in Stata, these density histograms that have the area under the curve of the bars adding up to 1, it's still somewhat counterintuitive, I think, to use them. And instead, if you really want to try to get a nice, smooth estimate of the probability density function for your variable, you should use kernel density estimation. Yeah, the only thing that histograms do that's really like even getting us close to the density curve for a true continuous variable is that they do this binning, which kind of gives us a sense that the heights of the observed values are representative data in that region. So they do some of this smoothing, although you can have discrete histograms that don't really have that binning. So you can make a discrete histogram for data that you think come from a continuous variable. So generally speaking, it's a good idea to use kernel density estimates instead. And I think I had a slide on that, but maybe I don't. So that'll be something I cover in a higher level class. Thanks everyone for watching.